MathStat341, day around 21, give or take. If we do a good job today, we will actually be ahead of schedule, and there will be no class on Friday. So we've actually got some time in the bank. Use that time to really look over the exams, to look over the stuff we've done, to read ahead, because the book, you might have noticed by now, we're going through it linearly. You read ahead, use that time. Okay, that's if we can get through enough today. So, moments in differentiating identities. So we've already talked about this. We've already seen the power of differentiating identities. And I apologize, we've been doing a lot of Star Wars references at home. When I start saying words like power, it just starts to go into a certain voice. Okay? But it is wonderful what you can do with differentiating identities. We've already done, I believe, the binomial distribution. Let's do the Gaussian. Now, one of the hardest things about differentiating identities is you need an identity. So we could start off with the integral from minus infinity to infinity, 1 over the square root of 2 pi e to the minus x squared over 2 dx. This is the probability distribution. And I want to find the moments. So I would want to multiply by x squared and integrate. Well, if I just multiply by x squared, I don't really have much that I can do because I have no free parameter. Anybody know what integration technique you can use to solve this?
U sub.
Okay, how would you do u sub?
Set negative x squared over 2.
So you could do u substitution, and if you do u substitution, it will eventually lead you to the gamma function. And we saw that in the baseball lecture. But you would need to know how to integrate the gamma function. It's not a bad thing to try, it's not going to work. What else could we try? Don't know many techniques.
Integration by parts.
Integration by parts. So you have to decide what is u, what is v. Now, if everybody's really quiet, so don't rattle your papers, don't drink your drink, don't write anything down right now, listen very closely. What is e to the negative x squared over 2 dx? What is it begging for? What does it want?
To be separated.
It wants to be, but what does it want? When you see the x squared over 2, what does it want to have associated to it?
X.
It wants an x. You know what? Let's just give it what it wants. So if you put it like that, notice now I can integrate that very nicely. If I let u be x and du is dx, if I let dv be e to the negative x squared over 2x dx, then v is just going to be negative e to the negative x squared over 2. And then I can do everything nicely. So the tricky part of doing this by integration by parts is that you need to know you have to move one of the x's to be next to the exponential. If you wanted to calculate the third moment, x cubed, how would you calculate the integral of x cubed times the density?
Do integration by parts.
No! You could do that, but no.
Could you do?
Nope. It's got to be, it's a real simple solution. You're integrating x cubed.
It's odd.
It's odd, right? So if you're integrating x cubed times the density, if the density is even, and this is odd, well, the integral of an odd function of a symmetric region is 0. So we don't have to worry about the odd moments. If you had to do x to the 4th, then you would just continue to do integration by parts. But if all you're doing is the odd moments, it's much easier. It turns out that there's a lot of great work, and if you want to calculate the expected value of x to the 2m, it is 2m minus 1 double factorial. That's the 2mth moment of the Gaussian. Wonderful result, and we've seen combinatorial interpretations of this. This is the number of ways of matching 2m people into m pairs of 2. So if you do things by induction, if you keep doing differentiation, you should be able to prove this. And that's a nice exercise to just roll up your sleeves and do the algebra. Given that this is the lecture on differentiating identities, I want to show you how we can do this by using differentiating identities. Now, the problem is you need an identity to differentiate. So even if I only care about the standard normal, I might have to consider more than one normal so that I have a free parameter. And that's the hardest part of all of this, is finding the right identity to look at. And so what I'm going to do is I'm going to consider a normal with variance sigma squared. Okay? So what do you think I want to differentiate with respect to? What's my variable that I'm going to differentiate with respect to? Sigma. I can't differentiate with respect to x. X is being integrated out. Ooh, what rule am I going to get to use because I have it like this?
Product rule?
You could do product rule or you could do quotient rule. They're the same.
Okay, yeah.
I don't want to use the product rule. I'm going to multiply both sides by sigma squared. Right? And then at the end of the day, I'll know that this is missing a sigma squared and I'll add that in later. But this just avoids having to use product rule or quotient rule. Now if I take the derivative with respect to sigma, I'm going to get a negative, I'll get an e to the negative x squared over 2 sigma squared, and then the derivative of this with respect to sigma. So I have the derivative with respect to sigma of e to the negative x squared over 2 sigma squared. This is going to be e to the negative x squared over 2 sigma squared. And then I need the derivative of this. So I'm going to get a negative x squared over 2. And then I have the derivative of sigma to the negative 2, which becomes negative 2 sigma to the negative 3. All right, the negative 2's cancel with that. And so I just get x squared over sigma cubed e to the negative x squared over 2 sigma squared. Oh, right? We're trying to calculate the second moment. When we take the derivative with respect to sigma, we get an x squared coming out. Life is good. Right? So we apply, let's say, sigma cubed d by d sigma. And when we apply that, we'll get the integral from minus infinity to infinity, x squared, 1 over the square root of 2 pi, e to the negative x squared over 2 sigma squared. I take the derivative of this with respect to sigma. So I get a 2 sigma. I multiply by sigma cubed, so I get 2 sigma to the 4. Is this right?
Did you use the first integral? Which says 6
Oh, wait,
sigma
wait.
squared?
When I move the sigma over to
Yeah.
the other side, this should be what?
1. Sigma to the 1.
It should be sigma to the first power. It was the square root of sigma squared. I'm looking at this and going, I know what the second moment of normal is. This isn't working. I had the wrong thing here. All right. What's the derivative of sigma with respect to sigma?
1.
1. And then when I multiply by sigma cubed, I get sigma cubed. Okay? And so this is almost the second moment. Right? What is it missing? It needs a sigma squared down here. Well, to get a sigma squared down here, since it's a square root, I need to move a sigma over. And so if I move a sigma over, I can make that a sigma squared, and then this just becomes now a sigma squared because I lost a sigma. And there is the moment of the Gaussian. And if you want to calculate more moments, then you would leave that as a sigma cubed and just keep differentiating. So I'll keep this over here. I'll move this back over here. It's the nice thing about being at the board. And when I take the next derivative, what's going to come down? We'll now have a 3 come down. Oh, yes, Joe. It really makes professors happy when we hear, oh, ah, go Red Sox. Things like this make our day. Okay? So when you take the derivative now, we're going to have a 3 come down. So when we do the next level, we'll have a 3 come down. It'll be sigma squared, but we multiply by a sigma cubed, so we'll have a 3 sigma to the 5th. What happens when we do it again? It'll be 5 times 3 times times sigma to the same. So really, I shouldn't write this as sigma cubed. How should I write this? Being very pedantic. 1 times sigma cubed. And now you can see the 2n minus 1 double factorial coming in. Right? There is a reason why I love differentiating identities so much. You can see it coming in. Okay. Any questions on the Gaussian? So now we just keep applying this to different systems. Okay. How many of you have seen the exponential function?
E to the power.
Well, the exponential probability distribution, the exponential distribution, the exponential random variable. Oh, good. There are 2 ways to define the exponential random variable. Are they both acceptable? No! One is terrible. It should not be used. If you go back to multivariable calculus, the physicists and the mathematicians often have a difference of opinion of how to have the angles for spherical coordinates. Does it really matter at one level? No. But when you're trying to read and understand things, it does. I was actually taught by the physicists, so I actually have trouble with the mathematicians because you go to what you learned first. So let's do exponential. I'm going to do, the density is going to be 1 over lambda e to the negative x over lambda. Right? Does this integrate to 1? Yes, use substitution. So note, the integral from 0 to infinity of 1 over lambda e to the negative x over lambda dx equals 1. What do you think I'm going to want to differentiate with respect to? Lambda. Now, am I going to be able to just conclude that all the odd moments vanish? No. In fact, this distribution is only supported on the non-negatives. The odd moments will clearly contribute. So we're going to take the derivatives with respect to lambda. Do we want to keep the 1 over lambda here, or do we want to move it over?
Probably easier to move it over.
I think it's much easier to move it over. Goodbye, move over here. Okay. So let's look at d by d lambda of e to the negative x over lambda. We would get e to the negative x over lambda, and then we'll get negative x. Then we have lambda to the negative 1, so we get negative 1 over lambda squared. The negatives cancel, so we're going to get a lambda squared. So what do you think we should apply? D by d lambda, and what would you put in front of the d by d lambda?
Minus 1 over lambda.
Well, the minus 1's cancel.
Then 1 over lambda squared.
If we put lambda squared,
You
then
want lambda
cancel.
squared, not 1 over lambda squared. When we take the derivative with respect to lambda, we get a lambda squared down below. So if I put a lambda squared above, it's going to cancel out that lambda. And when we take the derivative, we're going to get this extra fact of x floating. So when we apply that, we then get the integral from 0 to infinity of x e to the negative x over lambda dx is equal to, I take the derivative with respect to lambda and I get 1. And then I multiply by lambda squared, so I get lambda squared. We could do this integral by parts. It's not a horrible integral to do. But there's no need. This is integrating without integrating. And if you think this is good, wait till we get to chi-squared. It's amazing how much we can integrate without integrating. If I want to calculate the mean, so the expected value of x would just be the integral from 0 to infinity of x 1 over lambda e to the negative x over lambda dx, which would just be lambda. There is a group of people who actually write instead omega e to the negative omega x. And they might even use lambda for omega. I don't like this. Because here, the parameter is lambda. What's the mean? lambda. Over here, your mean would be 1 over omega. You know, I want my parameter to be the mean. I understand that. Is it wrong to do this legally? No. You know, we can't stop people from doing it. Okay? It's like going to Amherst. Okay? But there's better things you can do. And I would much rather use the negative x over lambda because I can look at that and I can see lambda is the mean. It's the expected number. All right, building on our success, what do you think we would want to calculate after calculating the mean? The variance. So we would have to apply it again. So if we apply it twice, well, when we apply it twice, what do we get? Well, we would get an x squared, because we get an x each time. We have to take the derivative of lambda squared, it'll be 2 lambda, and then we multiply by lambda squared, so we get 2 lambda cubed. Just making a mistake. It doesn't seem right. Oh, no, that is correct. That's correct. We get 2 lambda cubed. So now if I want to calculate the second moment, I have to remember I have to bring 1 lambda back to this side, so that's probability density. I'm missing that. It's going to be the integral from 0 to infinity, e over x squared, 1 over lambda, e to the negative x over lambda dx equals 2 lambda squared. So the variance is going to be the expected value of x squared minus the square of the expected value. So it's 2 lambda squared minus lambda squared is lambda squared. So what's the standard deviation? If the variance is lambda squared, what's the standard deviation? The square root of lambda squared.
So lambda.
Lambda. Very, very strange. Lambda is both the mean and the standard deviation. Okay? All right. Any questions about exponential? So all that I can do now is I just take any distribution that I like and I find a way to calculate the moments. Yes?
So like, does this only work out nicely for some like distributions though?
So the question is, as the distribution gets more complicated, could it become harder? I need a nice identity. As long as I have a nice identity, I can do the differentiation. But when I do the differentiation, what I get has to be close to the moment.
I see.
And so we were very lucky that these things over here are going to pop down in x with some powers of lambda. Powers of lambda don't bother me. I can deal with powers of lambda. But if I had, something like square root of x or cosine of x, then I'm in trouble. All right, so what I want to do is I want to start off with the geometric random variable and then go from that to the negative binomial. We've already done the binomial random variable and we've seen how to use differentiating identities. We had the x and y, we differentiated with respect to x, and then we set x equal to p, y equals 1 minus p. And we had to make sure we did that at the very end. All right. So do you think discrete is going to be easier or harder? Harder, why?
We can't integrate. Or we would need to modify to be able to integrate it.
So for the discrete? Well, instead of integrating, what do we do if it's discrete? We're not going to be integrating if it's discrete. What will we be doing instead?
Taking a sum.
Taking a sum. So we have to be able to do the sum. Fortunately, we know that if we have a probability distribution, what can you say about the sums of the probabilities? It has to be 1. So that's going to be the key to all the analysis. So let's consider a geometric. And the notation can be a little bit off. So there are two different ways of doing this. Do you want P to be the probability of a success or the probability of a failure? We'll do it as a success, and we'll see what happens. P equals probability of success. Okay? And then what we're going to do is we're going to keep tossing until we get a success. Toss until we get a success. So what is the probability that it takes exactly n tosses? Okay, 1 minus p
To the power of n minus 1.
to the power n minus 1 times p. And so now we want to calculate the expected value of x, and that's going to be the sum, and goes from what are the possible values of n? 1. Right, I'd be amazed if you could get ahead on your 0th toss. I'll wait till it's not recording. So n, 1 minus p to the n minus 1 times p. Now we need to start off with something that's known. Well, because it's a probability distribution, we know the sum goes from 1 to infinity of 1 minus p to the n minus 1 times p equals 1. Right? So we want to differentiate this. If I differentiate this with respect to p, I'm going to get an n minus 1 coming down. And I've also got a p here, so that's a product rule. That's fine, it's just a little bit of algebra. Right? This is the same as the sum, and it goes from 1 to infinity of 1 minus p to the n is equal to, I bring p over to the other side, and it comes down, add an n to the negative 1, it's a 1 minus p over here. And I could even write this, if I want, as 1 over p minus 1. Why do you think I want to write it as 1 over p minus 1?
It's easy to differentiate.
It's easy to differentiate. Remember, who is the patron saint of mathematics? New England Transcendentalist.
Thoreau, that's right.
Henry David Thoreau. Right? This is Williams. This is not a technical institute. We're supposed to be cultured here. Okay? I won't quite go to the point of assigning his readings. I did jog around Walden Pond, and unfortunately I was trying to act macho with my friend, and after we went around, I said, oh, that wasn't so bad. She goes, oh, shall we do it again? And I was much chastised after we finished the second time. Simplify, okay? Do we have to use the quotient rule? Hell no. And in fact, what's the derivative of negative 1? 0. So this is clearly going to be a much better derivative to do. You know, this is why I would much rather cover less material in the class and cover it well and really emphasize how do you think about things? How do you try to see what's going on? Well, now if I take the derivative, let's just do d by dt for now. I will get a sum and it goes from 1 to infinity of n, 1 minus p to the n minus 1. Oh, right? We wanted an n minus 1. Right? Life is good. And then we just take the derivative of 1 over p with respect to p. That's just 1 over p squared. And we'll have,
I think we also have a negative on the left side for the product, for the chain rule.
oh, good. I was about to say there has to be a minus sign. Good. 1 minus p to the n minus 1. And then we have a negative 1 here where we take the derivative of 1 minus p. I'm so used to having a p and not a 1 minus p, thank you. And now over here, we get negative 1 over p squared. And so now the two negatives cancel. This is almost what we want for the mean. It's missing a p. Not a big deal. So the expected value of x is the sum, and goes from 1 to infinity of n, 1 minus p to the n minus 1 times p is 1 over p. And there you go. The mean of a geometric random variable is 1 over p. So there are many lessons I want you to take from my class. When you see two numbers that are being multiplied, what should you do?
Take the log.
Take the log, right? If you're teaching fourth graders multiplication, no, but almost any other time, it's a good idea to at least think about taking a logarithm for mathematical things. Simplify. If you're not sure what the probability is, what could you do? Simulate. And if you ever have a formula, test it. Look at extreme cases. Can somebody give me an extreme value of p? 1. So if p is 1, this is known as the Mobius penny. It's one-sided. It always lands on heads. Okay? How long do you expect to toss it before you get your first head? 1. This is the heads I win, tails you lose coin. Right? So if p equals 1, good. The expected number of tosses is 1. What if p is 0? You have no chance of getting a head. How long will it take for you to get that head? And you see 1 over 0 is infinity. If p is a half, the fair coin, it's basically telling you you expect 2 tosses to get a head. A very reasonable answer. So for a geometric random variable, the probability of success being p, you expect to have to wait 1 over p before you get your first success. Okay. Any questions about the geometric random variable? We could have tried to differentiate this directly. We would have an n minus 1 coming down. We'd then have an n minus 2. We'd have a product. You could still do it. So this is where the subject is a bit of an art. Have I done the comparisons between factoring and the quadratic formula? Okay. Can somebody solve x squared minus 7x plus 12 equals 0? Okay, I actually have done x minus 3 and x minus 4, but how did you do that so quickly? I mean, you could just, so what if I give you, x squared minus pi x plus e to the gamma equals 0? Can you factor it for me that fast? No. So over here, you have an artistic way of looking at things. Can I see two numbers that multiply to plus 12 and whose sum is negative 7? And if I can see such numbers, boom, I've got it. If you can't see that, what can you do? Good. The quadratics are negative b plus or minus root of b squared minus 4ac all over 2a. We have a procedure we can just crank through. It's nice to have procedures you can crank through. It's nicer if there's a high-level approach that you can just look down and see, this will get me there faster. But it's nice to know that we will have a way. All right. Let's consider a generalization of this. So this is geometric. So we have the probability of success. I want to consider something a little bit more complicated. Toss until get successes. And I believe this is called the negative binomial. Can anybody give me a value of r that should be easy to understand?
Well, r equals 1 is
Good.
the case that we just did.
We just did r equals 1. So at the end of the day, when I get a formula for you, what should be the very first thing you do with that formula? Test for r equals 1. And if that doesn't work, then we've made a mistake somewhere. Either in the initial derivation here, or in what we're about to do. But again, always think, is there a case I know? All right. So let's try to calculate. What is the probability that x equals n. And then we have a lot of different ways that we can choose to write it. I could choose to write x equals n, or instead of writing n, I could write n plus r. I could write it as n plus r if I want. Because I know I'm not going to see r successes until I toss at least r times. And so if I do this, now n goes from 0 to infinity. In the other way, n would go from 0 to infinity, but the first few guys would all have 0 probability, and then once n gets up to r. This is very similar to saying, look, I know I needed to have at least r tosses. Why don't I write n as the excess? It all comes down to, at the end of the day, which is going to be better algebra. The last one we did, we actually didn't do it as n plus r, we just did it as n. I'm going to write it this way just to show you a different way of doing the algebra and see how things go. All right. So we have our tosses 1, 2, n plus 1, n plus r minus 1, and r. Are there any tosses whose results you know?
Well, for the final one, it has to be a success.
Has to be a success. Right? We know that has to be a success. What must be true in through here? So what do we know in the first n plus r minus 1? What must happen? How many successes, how many failures?
R minus 1 success.
So you have to have r minus 1 successes, and then you have to have n failures. How many ways are there to choose r minus 1 of these spots to be a success?
N plus r minus 1, choose r minus 1.
Right. N plus r minus 1, choose r minus 1. So that's the number of ways we can choose spots to be. Now for each success, that happens with probability p. And each failure, so we have 1 minus p to the n, p to the r. We need an identity. Anybody know what the identity should be?
Is it like the one from?
No. You will kick yourself once you see the identity. We need an identity.
Are we not doing the sum of it all equals 1?
Would you like to formally suggest that?
Okay, I would like to formally suggest that we add up them all and make it equal to 1.
All right, so you are claiming that the sum n goes from 0 to infinity of n plus r minus 1, choose r minus 1, 1 minus p to the n, p to the r equals 1. You claim that this is true. Can you prove this?
Well, if it's a probability
Yes!
distribution.
Right?
it has to be 1.
There's no proof needed. Because it's a probability distribution, it has to sum to 1. If you would like a really painful exercise, prove from first principles that this sums to 1. There's no need to do that. Okay, now we want to differentiate. Is there anything we should do before we differentiate? Sorry? Well, if we take the...
Oh, you should change the n plus r minus 1, choose r minus 1 into the equation instead of choose r
I'm sorry?
expression. You should put it into the fraction that it represents.
We could expand it out, but if we're going to have to deal with the factorials, it's going to become a very involved calculation. What do you think we're going to want to differentiate with respect to?
N?
Well, n is what I'm summing over. I can't differentiate with respect to n.
R.
R is fixed. It's the number of successes. We're running out of things.
P.
P, right? Why P? That's the one parameter that we have. When you differentiate identities, what's your parameter? For the Gaussian, it was sigma. For the exponential, it was lambda. For the negative binomial, for the geometric, it was P. Here, it's P. So when I differentiate this with respect to P, what gives me a little pause on this side? What's going to happen if I differentiate this with respect to P? What am I going to have to use? Product rule. How can I eliminate the need of the product rule?
Move over the P to the R.
Right, can I move over the 1 minus P to the N? No, because N is an index of summation. So I hope you will accept as a friendly modification moving a P to the minus R over. Do you accept that as a friendly amendment to your identity? You made the motion. I have to ask you, do you accept this as a...
Yeah, I would accept this.
All right. I don't think this is exactly what we want to look at, though. Because we want to calculate the expected value of x, which is going to be the sum, n goes from 0 to infinity, of n plus r, right? Times the probability that it equals n plus r. So n plus r minus 1, choose r minus 1, 1 minus p to the n, p to the r. Now the p to the r we can deal with later, but we want to get a n plus r. If I take the derivative of this with respect to p, I'm going to just get an n coming down.
Oh, so, and then we can multiply both sides by 1 minus P to the R.
Yeah, so if we accept that as a friendly amendment, we multiply by 1 minus p to the r, and we'll get p to the minus r, and then 1 minus p to the r. And now when I differentiate this, I am going to get an n plus r coming down. And then I'll play games at the end of fixing things. And in fact, I can even write this as 1 minus 1 over p, if I want, to the r. Did I do it right?
I think it's the other way. Like 1
No,
minus
it's,
P.
it's the other way. It's 1 minus p minus 1. 1 over p minus 1 to the r. Just to try to make things a little bit easier for me when I take the derivative, I don't want to do the quotient rule. So if you take this as your identity, and it was a little bit of work to find this. This is now better situated. So now we apply d by dp to the sum, and goes from 0 to infinity of n plus r minus 1, choose r minus 1, 1 minus p to the n plus r, and that's going to be equal to 1 over p minus 1 to the r. So when we take the derivative, we get the sum. Let me make sure this focus is not. Okay. So when we take the derivative, we get the sum n goes from 0 to infinity of n plus r minus 1, choose r minus 1, 1 minus p to the n plus r minus 1. And now on this side, I take the derivative with respect to p, and I'll get r, 1 over p minus 1 to the r minus 1. And then the derivative, oh wait, I keep forgetting the damn negative sign from this, right? So I have the negative 1 from that. But when I take the derivative of this, I'll get a negative 1 over p squared. So the negative sign will cancel. And now it's all about just collecting the algebra. So what do I want? I want a 1 minus p to the n. I have a 1 minus p to the n plus r minus 1. That's not a big deal. So I'll just move a couple things over. It's the sum, and it goes from 0 to infinity of n plus r, n plus r minus 1, choose r minus 1, 1 minus p to the n. Now over here on this side, I have an r. This is going to be 1 minus p to the r minus 1 over p to the r minus 1. And then I have a negative sign which cancels. I have a p squared. So this is going to become an r to the p to the r plus 1. I want a p to the n here, so I have to divide by p, 1 minus p to the r minus 1. So over here I put a 1 minus p to the r minus 1. Does this make you happy? Yes. And I want a p to the r over here, right? I need a p to the r, so I have to multiply p to the r. So I have to multiply this by p to the r. Oh look, the p to the r cancels. And when the dust settles, it's r divided by p. When r equals 1, does it work? Yes. Okay, so this is a good start. If you want, try to prove directly the mean. You might be able to by manipulating factorials. To some extent, doing a calculation like that is good because it will make you appreciate the power of the differentiating identities. You need to really experience just how bad life can be to really appreciate why differentiating identities is so wonderful. You need to be able to find the identity. The identity can often be hidden. Continuing the Star Wars theme, who was the hidden Jedi? In episodes 4, 5, and 6.
Yoda?
No.
No.
No. Well, they were both hidden. But there was someone hidden from Vader.
Luke?
I would have accepted Luke or really his sister. And then Luke slips and mentions that, oh no. He goes, oh, you have a sister. And then in a wonderful family relationship, he then goes to try to either kill or turn his sister or his daughter to the dark side. But she was hidden. The identities are often hidden. And you often have to spend a lot of time working. Then you have to sometimes spend some time rearranging things to make the algebra nicer. You don't have to do this. You could do the product rule, and you would have two infinite sums that you would have to play with. I think it's much cleaner to do it like this. And then, once the dust settles, say, okay, what do I need to multiply it by now to make it look like the expected value? So first get something that's simple, take the derivative, and then go backwards. Now, we still have 5 minutes left, though. So there's got to be something more to say about this problem. So the question is this reasonable? That it should be r divided by p.
Yes. If you look at the geometric distribution,
Okay.
it's like a sum of r geometric.
Excellent. So make sure, everybody who's been making comments today, please make sure you keep emailing me. So consider x1, x2, dot, 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 x, r, are all geometric with parameter p. We saw this with a binomial. Right? What is a binomial except a bunch of Bernoullis? You have a bunch of independent tosses. So what we're going to do is we have a bunch of geometric random variables. What does it mean to keep going until you have r successes? Well, it's a geometric process until we get the first success. From that point onward, does it matter what happened? No, it's a new game. So what is, let's say x is x1 plus xr. What is the expected value of x?
So, with linearity of expectation.
By linearity of expectations, one of my favorite results in all of mathematics. The expected value of a sum is the sum of the expected values. Each of these have expected value 1 over p. Noting this, was there any need to have done the calculation on the board for the negative binomial? Yes or no?
Yes, for education.
Yes, for educational purposes, thank you. There was a reason why we did this. It wasn't just, holy shit, I just realized like with 5 minutes to go, wait, there was no need to do this. We could have just done the following. Or that there's not enough material to fill up an entire semester of 341. Right? This is a really good problem here in terms of how do you handle the algebra? And that is the hardest part. So at some point I will be doing Rubik's Cube lessons for people who want to learn. I lent somebody a 2x2 yesterday. Here is, a little bit bigger one. So, a lot of life you realize very quickly is showmanship. Oh, you do Rubik's Cubes? Well, how many sides? Oh, 6 sides. Oh, how quaint. This one has more. So one of the questions you always want to get a sense of is, how complicated is a cube? So how many pieces do you have on a 2x2 cube? You have 8 pieces on a 2x2 cube. How many on a 3x3?
27.
Nope.
Oh, the middle one doesn't count.
The middle one doesn't count. So how many do you have?
26.
One extra credit point. Wait. -1 for the Hebrew God? What movie? Indiana Jones and the Last Crusade. The staff was burned onto the Germans, the medallion on his hand, and he didn't realize that there was writing on the back that said subtract 1. If I give you an n by n by n cubed, it's n cubed minus n minus 2 cubed. If you have a 4x4 cube, it's the same as 4x4 where you have everything, and then you subtract off a 2x2 center. So actually, when you look at this in terms of how it's going to grow, it's actually going to grow quadratically in terms of the number of pieces. So when n equals 3, that gives you 27 pieces. Minus 1 is 26. How many sides does this have? 12. Has 12 sides. Each piece is on exactly 3 sides. Each side has 5 pieces. So if I want to figure out for the duodecahedron, the number of pieces is I have 12 sides, each one has 5, but that counts each piece 3 times. What does that equal? 20. And when n equals 2, you actually get 8. So in terms of piece count, there's actually fewer pieces on this than on the 3x3. More sides, but fewer pieces. It turns out you don't need to know really much more than just solving a 2x2 to solve this. You essentially make this like the bottom layer. But it can be hidden, and the cubes are wonderful at hiding things. The reason I wanted to go through and do the long calculation is if you can check something multiple ways, it's good. This not only allowed me to show you how to do the method of differentiating identities, but it gave me a problem where at the end of the day, I know what the answer is. And so I can then be confident we've done the algebra correctly. In Math 150, how many of you have done Green, Gauss, or Stokes theorem, one of the big 3? So the trick is, earlier in the semester, if you're doing line integrals or stuff like that, we often give you problems where the curl is 0, so that those of us who are the professors know that the answer should be 0, and you can just quickly check the work. And there's just a way to do it. The observation that this is a sum of geometric random variables means we can bypass all the calculations. It's similar to how when we attack the binomial, we could understand the binomial through the Bernoulli. So this is another general principle. Start with something small and simple, build up from that. All right, so this is a good place to end. Because we did so much today, and we had put some stuff in the bank, we actually did the 2 lectures of differentiating identities in one day. There will be no class on Friday. Use that time to make sure you understand what we've been doing and to just get